For 4n plus 1 equals x squared plus y squared, what do 4n plus 2, 2n plus 1, and n look like? In previous videos, we developed a few methods for finding the representation of primes of the form 4n plus 1 as sum of two squares, most of them relying on an infinite descent technique. One of them refining Harold Edwards' approach based on Euler's two-square theorem. Another one, an original descent that interestingly ends up mirroring Charles Hermite's simple continued fraction method. We also introduced a third approach that could possibly be Fermat's own infinite descent procedure, though he never published it. In addition, we presented a particularly elegant formulaic solution using elementary symmetric polynomials. In a later video, we connected Gauss-Eureka theorem and one of Euler's corollaries to the sum of two squares theorem, deriving the identity that expressed n as a sum of two triangular numbers, which we then extended to sum of 4 and 8 squares, examining them through the lens of Hurwitz's theorem, and including an analog of Fibonacci-Brahmagupta's identity for triangular numbers. In this video, we'll explore a few modest yet genuinely surprising gems hiding in plain sight within the theory of sum of two squares. We'll develop their specific algebraic expressions, but more importantly, we'll illustrate how number theory's magic often unfolds by casually playing with numbers and simple structures, and expected patterns begin to surface, patterns that at first seem surprising, but gradually reveal themselves as almost inevitable. Once you know that primes of the form 4n plus 1 can be written as sum of two squares, it's natural to start playing with integers and algebraic structures that interact well with such sums. That is, simple structures like the formula for Pythagorean triples or Fibonacci-Brahmagupta's identity. Another line of exploration is to express that same prime 4n plus 1 as a difference of squares. Now we got a prime that is both a sum of two squares and a difference of two squares. What can we pull from this algebraically? Let's start with an example and then try to formalize the patterns we find. Let's examine prime 7933, which equals 78 squared plus 43 squared, which can also be expressed as 3967 squared minus 3966 squared. We can rearrange the equation in two ways. On one side, 3967 squared minus 78 squared equals 3966 squared plus 43 squared. On the other, 3967 squared minus 43 squared equals 3966 squared plus 78 squared. Factoring the differences of squares and knowing that each resulting term must be a sum of two squares, we obtain 4045 and 3889 on one side, and 4010 and 3924 on the other. Once we compute the square decompositions, a surprising pattern emerges. Not only are the values repeated, albeit in a different order, but the components of each sum differ by exactly one, that is, 61 and 60 and 18 and 17. Intuitively, the recurrence of the values 61, 60, 18, and 17 feels almost inevitable. After all, the prime 7933 admits only one decomposition as a sum of two squares. If these values were radically different or far apart, certain combinations could potentially contradict that uniqueness, or worse, cast doubt on the number's primality itself. We'll see further evidence of this in the following slides. As for now, there are clear signs of an underlying structure. Simple combinations like 61 plus minus 17 and 60 plus minus 18 already hint at a hidden logic. Here's more evidence. Since we're dealing with products of sum of two squares, we compute both possible decompositions. For the left equation, one solution is expected: 3966 squared plus 43 squared. but the other, surprisingly, involves the same numbers by which 7,933 itself can be expressed as a sum of two squares, that is, 78 times 43 squared plus 2,117 squared. The same happens on the right-hand side equation, although this time the second square is 2,118 squared. We are already uncovering some unexpected patterns. And if that hasn't surprised you yet, just wait. These same values, 61, 60, 18, 17, and even 2117 and 2118 will keep reappearing in striking ways in the rows as sum of squares. Let's take a closer look at why these values keep reappearing, starting with an analysis of the following two equations. We already know that any factor of a sum of two squares must itself be expressible as a sum of two squares, so these brackets must follow the pattern. That gives us a pathway to express the structure more formally in terms of p, x, and y. Following a few short steps, we find that each bracket is half the sum of two squares, and we can show that this too is expressible as a sum of two squares. When x is even and y is odd, then both terms are integers. If x is odd, we can write x plus minus 1 as 2 times u, and y is even, then y equals 2 times y sub 1. Thus we got 2 times the sum u squared plus y sub 1 squared, which equals the square of u plus y sub 1 plus the square of u minus y sub 1. Or if you prefer to express it directly in terms of x and y, we get these two squares. Still, we should admit it's not as tidy as one might hope, and it gets messier when we bring in the second equation. So let's try a different approach, one we already explored in an earlier video. In a previous video, Triangular Numbers and Herwit's Theorem, we presented an identity for primes of the form for n plus 1 that connects sum of squares and sum of triangular numbers, where a and b can have any parity. Here, we will use a variation instead. See how 61, 18, 60, and 17 fall into place within this algebraic structure. So by defining x equals a plus b minus 1 and y equals a minus b, and applying in those brackets, we find that the first one becomes a squared plus b squared, and the second one becomes a minus 1 squared plus b minus 1 squared. Thus, we arrive at a reformulation of the original equations in terms of a and b. Just as we did with the equation on the left-hand side, we can apply the same procedure to the one on the right. The steps remains identical. The only difference is the terms in each bracket. Let's now turn to these other two equations. Using the squares we previously identified, namely a minus 1, b, and b minus 1, when we apply Fibonacci's and Brahmagupta's identity, we can see how x squared plus y squared minus 1 over 2 and y or x are the squares in the first solutions, and that x times y and x squared minus y squared plus minus 1 over 2 are the squares in the second solutions. We'll now display the corresponding identities in terms of a and b for the first set of equations. Here, for the second set of equations, feel free to pause as needed, and the third and fourth sets of equations. So far, we have uncovered a wide range of unexpected equalities expressible in terms of x and y for primes for n plus 1. Many of these identities take on a more elegant form when rewritten in terms of a and b, using the substitutions x equals a plus b minus 1 and y equals a minus b. Now it's time to return to the initial questions. Given 4n plus 1 equals x squared plus y squared, what do 4n plus 2, 2n plus 1, and n look like? We have already found how to express 4n plus 1 and 4n plus 2 in terms of a and b, as shown below. Finding how to express 2n plus 1 is straightforward, since 4n plus 2 equals 2 times 2n plus 1. And in the sum of squares a, b, a minus 1, and b minus 1, we necessarily have two even integers, say c and d, and two odd integers, say e and f. Then c squared plus d squared is 2 times the sum of these squares, and e squared plus f squared is 2 times the sum of these other squares. So we get the sum of these 4 squares as 2n plus 1. So when a and b minus 1 are odd, 2n plus 1 has this form. Note that one of the squares happens twice. And when a and b are odd, 2n plus 1 has this other form. Here also, one of the squares happens twice. Finally, what does n look like? Since the square of a minus b plus 1 over 2 can be written as a sum of these three terms, when a and b minus 1 are odd, then we can replace it in 2n plus 1 above, thus deriving n as the square of a plus b minus 1 over 2 plus the square of a minus b minus 1 over 2 plus a minus b minus 1 over 2. Similarly, when a and b are odd, since the square of a plus b over 2 can be written as a sum of these three terms, then replacing that in 2n plus 1 above allows us to derive n in this other way. Summing up, we visualize how to express 4n plus 1, 4n plus 2, 2n plus 1, and n in terms of a and b. Finally, we will visualize how these same forms look like, this time in terms of x and y. Here you can see neatly all the equations just in terms of x and y. In conclusion, to illustrate how number theory's magic often unfolds, we chose not to begin with identities followed by examples. Instead, we started by casually playing with differences of squares and combining terms, leveraging Fibonacci-Brahmagupta's identity, and in doing so uncovered numerical patterns that felt surprising at first, yet soon came to seem natural. This presentation uncovered a few modest yet genuinely surprising gems hiding in plain sight within primes of the form x squared plus y squared. We developed specific algebraic expressions for 4n plus 1, 4n plus 2, 2n plus 1, and n, not only in terms of x and y, but more elegantly in terms of a and b. In fact, beyond elegance, evidence increasingly suggests that this expression that connects sum of triangular numbers and sum of squares is pervasive in describing primes of the form 4n plus 1. This structure has surfaced naturally in a wide range of contexts, proving the formula for Pythagorean triples, linking Gauss-Orega theorem with Euler's sum of two square theorem, as shown with this identity, exploring analogues of the Fibonacci-Brahmagupta's identity for triangular numbers, and extending triangular number properties to sum of 4 and 8 squares. See our previous video, Triangular Numbers and Hurwitz's Theorem, for more. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.